Hey there, let's talk about metallic bonding. We're going to start just with a quick reminder of what the properties of metals are. So metals will conduct electricity as a solid. They're typically shiny and they're malleable, so you can bend them. And we say that they're ductile, they can be drawn into wires. We're really familiar with metals because we have just pure metals all around us, from our metal spoon to the wiring in our house. So these properties are familiar. It turns out the reason that metals have these properties is because of the way their atoms are held together. So let's talk about that next. Okay, metallic bonding. When we talk about a metal, you know you just have a whole bunch of atoms of that metal. So if I have something like magnesium metal, a piece of magnesium ribbon, that's a whole bunch of Mg atoms all grouped together. And so if I wanted to draw a picture, I might draw something like this. Now, these metal atoms are actually arranged in a crystal lattice. And a crystal lattice is a three-dimensional regular arrangement of atoms. And when you try to kind of picture what a crystal lattice is, think maybe of an array of oranges at the grocery store when they have them stacked in that nice pyramid where all of the oranges are arranged in a nice little tower and they're all relative to one another, that kind of thing. So you've got all these metal atoms in this crystal lattice, and we'll talk more about this in class and give you some more visuals and those sorts of things. But the question is, what's holding them together? I mean, if you think about bringing a neutral atom with another neutral atom, there's nothing that seems like it would be attracting. Okay, but if you look inside of your magnesium atoms, there are positive and negative charges. And those positive and negative charges are what we're going to use to actually create the glue or the attraction that holds your piece of metal together. Consider magnesium's orbital filling diagram. 1s2, 2s2, 2p6, 3s2. Okay, if you look, this outer shell of electrons, the 3s and the 3p, this outer shell that is farthest from the nucleus, there's only 2 electrons in it. And those are pretty far from the nucleus compared to all the rest of the electrons. Something that's pretty far from the nucleus is going to be easier to remove. We talked about that when we talked about photoelectron spectroscopy. So these guys are going to be pretty easy to remove. What ends up happening is that every magnesium atom in this crystal lattice loses its outer 2 electrons, leaving behind a nucleus that has a +2 charge. Well, not really a nucleus at that point. A core, that's more accurate, that has a +2 charge because it's the nucleus and all of the inner electrons. And so you have all these +2 magnesium cores, and then those 2 electrons that were relatively easy to be lost, all of those electrons go into what we call the electron sea. It's basically a smear of electrons all over the core, all over the magnesium. You say, what? I know. So these electrons are going to be shared by all of them, all the magnesium atoms. We say that this is a non-directional bond because the electrons are actually being attracted to all of those positive magnesium charges. Because if you think about these electrons that are in this electron sea, ooh, I should definitely write electron sea, and so should you. So we have our outer, also called valence electrons, being attracted to all of those positive cations, those positive cores, to our atoms, to our metals. So where's the positive and negative attraction? Well, it's the electrons that have been lost from the outer or valence shell of the magnesium being attracted, so those are negative, right? Being attracted to all of the remaining positive magnesium ions. An ion is an atom with a charge, remember. So we have negative electrons being attracted to positive ions. And so I have a positive-negative attraction. And every type of bonding we're going to talk about, it always comes back to having a positive and negative attraction. That's what holds your metals together. That's what holds all the compounds together. In this case, it's those electrons that are being lost to the being lost to the electron sea and being involved in non-directional bonding, so being attracted to everything. all the different atoms around it. Let's think for a second about how this is going to lead to the properties that we see. Focusing on conduction of electricity. Since these electrons are not attracted to any particular magnesium ion, but all of them, all of those core magnesium atoms, it doesn't matter where they are. So they can very readily move. So one of your electrons can move throughout your piece of magnesium. Flow of charged particles. You have electrons that, because they're involved in this non-directional bonding, are able to move throughout the entire piece of metal. Moving electrons, moving charge, is going to give you electricity conductivity. And so this works. The fact that it's shiny, the fact that they're malleable and ductile also play a role here. Being shiny, that's light interacting with those electrons that are free to move. Being malleable and ductile, you can move the atoms relative to one another because they're still part of the electron sea. By moving them, you do not interrupt those attractive forces that are holding your metals together. So metals have metallic bonding involving an electron sea, made up of the valence electrons from the metal atoms being attracted to the remaining positive core of those metal atoms.